Hello, everybody. Well, we started in chapter 3, we started the topic of determinants. And, as you know, in previous chapters, we did elementary, amongst other things, we did elementary row operations. So, so today we're going to do determinants and elementary row operations. And we're going to see maybe there's a connection between these two concepts. So maybe somehow these two things affect each other in some way. Anyway, that is what section 3.2 is all about. So let's go right to example 1. This is going to shed a lot of light on a lot of stuff. So in example 1, you'll notice A is the matrix 2, -3, 1, 4. But you see it's written just with straight lines. So that means the determinant of A. The determinant of A is 11. Now, if I take matrix B, now matrix B is the same as matrix A, only the two rows were switched. You see what I did here? I switched the top row and the bottom row, and I got matrix B. And notice the determinant is -11, and just multiply it out. You'll see, 1 times -3 minus 2 times 4, that's -3 minus 8, which is -11. Here, it's 2 times 4 minus 1 times -3, so it's 8 minus -3, or 8 plus 3, which is +11. Now let's do another example. Matrix B is obtained by matrix A by adding 2 times the first row to the second row. So here's my row 1, -3. Here's my other matrix 2, -4. And as we typically do, we want to turn that into a 0. It's a very typical thing to want to do with matrices. So we did a row operation where we added -2 times the first row onto the second row. Very standard thing. Now, if you notice, when we did that, the determinant of the two matrices are exactly the same. That's 2 and that's 2. See, nothing changed. Now, finally, in matrix B was obtained from matrix A by multiplying the first row by 1/2. So 2, -8, -2, 0. The bottom row, -2, 0, that stays the same, or whatever it is, I can't see it. The bottom row stays the same. And the top row, instead of 2, -8, becomes 1, -4. And when you take the determinants, 1 times 9 minus -2 times -4, which is 1 minus 8, which is 8. So notice that the determinant here is 1/2 of what it was over here. So I multiplied by 1/2, and my determinant got shrunk by 1/2. And these now, just showing examples of something doesn't prove it, but these actually are examples of what does indeed happen all the time. And we're going to state it here in Theorem 3.3. So Theorem 3.3 says that if A and B are square matrices, then when B is obtained by interchanging two rows, it makes the determinant negative. If I add a multiple of a row onto another row, it keeps the exact same. It does not change the determinant at all. And if I multiply a row by a non-zero constant, then the determinant of A is going to be equal to that constant. I mean, the new determinant is going to be that constant times the old determinant. And that is just about. By the way, number 3 here, that's true even if I multiply by a 0 constant, as we're going to see. But I can't imagine why anybody would ever want to multiply by a 0 constant. That's why multiplying by a 0 constant is not part of the elementary row operations and so forth. Anyway, let's prove, let's at least partially prove this. So we're going to prove this. We're going to prove part 1 using a 2x2 matrix. And the rest of it is not that hard to prove. Okay, so here's A. Matrix A is A11, A22, A21, A22. Now matrix B, we just took the top row and put it on the bottom, and the bottom row put it on the top. Now the determinant of A, let's just multiply it out. That's A11, A22 minus A21, A12. The determinant of B is like the reverse of that, A21, A12 minus A11, A22. So you just go like that and go with it. And so clearly, The determinant of B is just the exact opposite, meaning that when I say opposite, I mean the negative of the determinant of A. Well, that's the proof for a 2x2. And once you know for a 2x2, give it, especially since determinants are built on each other, like the determinants are I'm going to say defined kind of recursively, meaning that the excuse me, the way you find the 3x3 is by taking a bunch of 2x2s, and then we'll find a 4x4 is taking a bunch of 3x3s. So basically, we could prove by induction, as we outline right here, that this will work. Once it works for 2x2, it's going to work for 3x3, it's going to work for 4x4, it's going to work for 5x5, so on and so on and so forth. And that is the way we prove this by induction. Now, this theorem 3.3, besides being a great theoretical interest, I find it fascinating. It also has a lot of practical because if you want to find the determinant, then you could do it's much easier to do some elementary row operations to get the matrix down smaller and get more zeros in there, and then and then you take the determinant of that easier small matrix, just multiply by the constants that you use, or revert whatever, divide by the constants that you use. You see what I'm saying? Well, let's just go through. You'll see what I mean. I think you understand what I mean. Anyway, so we saw this matrix given it 2, -3, 10, and so forth. And we're going to interchange the first two rows. Now, when you interchange two rows, that makes it negative. See, so we put a little negative over there. The next thing we're going to do is we're going to add -2 times the first row onto the second row, because we want to get rid of this 2. We want to get rid of that 2 over there. But we know that when you add a multiple of one row onto another row, it does not change the determinant at all. So power like this. Then we're gonna multiply the then we're going to multiply. Wait, let me just raise up a little bit so you can see better. Then we're going to factor out a factor of 7 from the second row, and we're going to factor out a factor. I'm going to factor out a factor of -7, because I want to turn that into a 1. Then I'm going to factor out a factor of -3 from the bottom row. That's what we did right here. I mean, one of this matrix right here. Well, here we have a triangular matrix. So here we have negative. I got negative. I have the negative here already. -1 times -7 is -3 gives you 21. And this here, I could just do this in my head because it's a triangular matrix. And a triangular matrix is you just multiply down the diagonal, but the diagonal is all 1s. So it's just going to be -21 times 1. This is going to be the final answer is going to be -21. -20, and we're writing it out. -21 times 1 times 1 times 1 is -21. But by doing a couple of operations, which are pretty easy to do, and this is a lot easier than going through all those cofactors and all that garbage. Remember all the stuff we did in 3.1? What garbage. But we had to do all that hard work in 3.1, so you really can appreciate how much better this is, now in 3.2. So now 3.2 is like, wow, it's going to save us so much work. And before I want to just go on, what if I know what you're all thinking right now? You're thinking, gee, we're doing all these elementary row operations, we're moving rows around. What would happen if we moved columns around, switched columns, or what if we did that instead of rows? What would happen then? Well, the exact same thing would happen. Sometimes we do want to do elementary column operations, and we call it elementary column operations. And if two matrices are, if I columnize one matrix to get another matrix, then the new matrix is called column equivalent to the old matrix. And turns out that 3.3 is 100% true and correct. If I would take the word row and just replace it by the word column, I would have the exact same result. Meaning, if I switch two columns, I make the determinant negative. If I add a multiple of a column to another column, and so on and so forth. Anyway, so where are we here? So this is, for example, here's my original matrix, and now I'm interchanging the first two columns. Why? I just decided to do that. But it's going to actually help us. Once I interchange the first two columns, by the way, it's already a lot easier, because 1 times 4 times 2, that's 8 times -1. See, I created a triangular matrix just by switching these two columns. And so the final answer is going to want to be -8. But let's just go through. But if you want, you could factor out a 2 from the bottom, and that and that turns this. Excuse me. If I would factor out a 2 from the bottom, this 2 here would turn into a 1, and it'd be a -2 out there. So it'd just be -2 times 4 times 1 times 1 times 4 times 1, which is the same -8. Anyway, look at this. Here's another example. We have 2, 3. This matrix right here is a new matrix, a brand new matrix. And what I'm going to do here is I'm going to factor out the 2 from the first column. And now my column, instead of 2, 4, -2, becomes 2 times 1, 2, -1. And which already, just having smaller numbers helps you. And you could even do more here. I could add 2 times, for example, I could add, I could keep going here and make this reduce even more. For example, well, okay, let's move on. Now, let's find a determinant using elementary column operations. So I really would want you all to do is to work on this by yourself. See if you can get it. See how far. See. Now, of course, you could always find the determinant just by doing the horrific cofactors, but we could also do the elementary column operation thing, and that may help us a lot. So let's do that. So pause the video, work it out. Okay, time's up. Now you're back on the air. So the first thing I did is I added -2. I added +2 times the first column onto the second column. Now, when I did that, the second column became all zeros. Well, guess what? You could stop at this point. We're done. The answer is that the determinant is 0, because if I want to do let's say I now decide, okay, I'm going to do the cofactor method. Well, I could do the cofactor method down the second row, and that's it. It's just going to be 0, 0, 0, 0. There's too many zeros there, but you get my point. It's just going to be so it's just going to be 0. So sometimes you do one simple little row operation or column operation, and pow, you've got your answer. That's pretty awesome. You see 0, 0, 0, pow is just 0. Now, this leads us to the following theorem, which is quite important. Matrices with 0 determinants. Well, if you have a matrix that has an entire row or an entire column consisting of zeros, then the determinant will be 0. And that makes sense. Like we said, you're just going to, when you do the cofactor method, either go across that 0 row or go up and down or go down that 0 column, and you're gonna just get zeros. Also, if 2 rows or 2 columns are equal, it's kind of a 0 determinant. But then again, that's simple, because if I have 2 rows that are equal, I subtract one from the other. I'm going to get a row of all zeros, which has a 0 determinant. And if one row or column is a multiple of another row, well, let's say one row is double another row. Well, I just add -2 times the smaller row onto the other row, get a row of zeros. So really, I mean, pretty much it's all, this all pretty much boils down to this guy right here, and it's pretty straightforward because you do the cofactors and pound. Okay. Anyway, if I have here's just 3 examples. So here we have a matrix with all zeros in one row, determinant is 0. Here we have a matrix where I have 2 rows that are the same, determinant is 0. Here I have a matrix with the 2 columns that are multiples of each other, because if you notice, the third column is -3 times the first column, because -3 times 1 is -3, -3 times 2 is -6, and -3 times -2 is +6. So again, these are just great examples. Okay, here's a matrix. Example 4, we're going to give you now an example of a matrix with a 0 determinant. So let's see how we get that. Well, what we do is if we add -2, sometimes you have to do a little work. Sometimes you have to do a little work with the matrix before that appears. I'm going to add -2 times the first row onto the second row. So my 1, 4, 1 stays the same. My 0, 18, 4 stays the same. But now the 2, -1, 0 becomes 0, -9, -2. Now notice how the bottom row is -2 times the middle row. Well, that's going to be enough. You see, now I could go further. I could add 2 of the middle row onto the bottom row and get zeros on the bottom if I want. And you can see it that way. But once I recognize it, that's it. We're done. Now, a lot of you may be saying, "Well, who cares? Easier, schmeezy. Who cares? I'm going to use calculators and computers and do all this." Well, even calculators and computers, easy makes a difference. Look over here. You see, if you have a determinant, a 3 by 3 determinant, and I want to do it with the cofactor expansion that we learned in 3.1. So it's going to involve 5 additions and 9 multiplications. If I do it with row reduction, which is what we're learning now in 3.2, it's going to be 5 additions, 10 multiplications. Oh, it's actually going to take an extra step. Sorry, chumps. But once I get a little bit bigger, let's say I go by a 5 by 5 matrix. If I do it the cofactor way, I get 119 additions and 205 multiplications. If I do it the row reduction way, which is what we're learning now in 3.2, it's only 30 additions and 45 multiplications. Now, even for a computer, this starts to make a difference. Let's say I have a 10 by 10 matrix. If I do it the cofactor way, the old-fashioned way, it's 3 million. It's over 3 million, 3.5 million additions and 6 million multiplications. Whereas if I do row reduction, to get it into triangular form, then it's going to take me 285 additions and 339 multiplications. Now, for a computer, a million, you're talking here like 10 million between the additions and subtraction and multiplications, it's only like 10 million steps. So this method here is 10 million. Now a computer can do 10 million steps pretty quickly, but 10 by 10 matrix is not that big, and you could easily get a 20-20. You can get a 20 by 20 matrix or a 50 by 50 matrix. You see what I'm saying? It gets to the point where it's ginormous. Let's see what it says here. In fact, the number of additions alone for the cofactor expansion of an n by n matrix is n factorial minus 1. And 30 factorial is 2.65 times 10 to the 32nd power. That's a 2 followed by 2.65 followed by another 30 zeros. That's a huge number. And that's just for a 30 by 30 matrix, which is not a gigantic. I mean, for our class, that would be a lot. If I would give you a 30 by 30 matrix for homework, that would be a lot. But in the industry, in actual real whatever, that's not that spectacularly big. So this what we're doing in 3.2 is essential. Besides being, again, a great theoretical interest, which personally I do find it a great theoretical interest, it has tremendous practical ramifications. And okay, let's do a couple of determinants. Let's find the determinant of this matrix right here. So actually, let me go down like this. So don't look at, oops, don't look at anything. Here's this matrix A. Oops, this matrix here, right here. That's A. So pause the video and solve it. Okay, unpause and let's go. So first I'm going to cap. I always look for the zeros. I'm always looking for zeros, and I want to capitalize and try to create another zero if possible. So what I'm going to do, is add. Now notice that I have a -3 and I have a +6. If I add twice the second row, twice the first column onto the third column, then what I get is that the third column becomes -4, 3, 0. So now I have 2 zeros in this column, and I already at this point, you know, I could, I'm ready to just forget, fooling around. And since I have 2 zeros, I only have one number in this bottom row. I'm going to just do a cofactor, or just do one cofactor. So it's -3 times this matrix up here in the upper right. And it's going to be -3 times +1 times the determinant of 5, -4, -4, 3. And that's really easy because that's just 15 minus 16. So it's -3 times 1 times -1, which is just 3 pound. But it was much, much, much easier from that. All I had to do was because I don't necessarily have to, even if you don't go all the way to put it into row echelon form, or I'm sorry, triangular matrix form, or yeah, well, triangle matrix form, which then you can turn that into row echelon form. Anyway, so even if I don't go all that far, just doing one step, just doing one, column addition made a huge difference. Now I only have just one little 2x2 to work out. So this is very, very powerful, very powerful. Now I know you're upset that I never gave you a 5x5 matrix to figure out, but I'm going to make amends right now. I'm going to give you a 5x. Oops. I'm going to give you a 5x5 right here, and that's what we're going to do right now. So I want everyone to pause the video, pause the video, and solve this. Okay, now unpause. Let's go through it. Okay, so the second column already has 2 zeros. See, there's a 0 there and a 0 there. So let's harp on that second column a little bit. Let's harp a little bit on that second column. So I'm going to choose it. So I want to do the cofactor expansion along that second column. Well, let's make it even nicer. Let's get a few, let's be greedy. Why settle for 2 zeros when we can get more zeros? So what we're going to do is that I'm going to, so in my greedy stage, I'm going to add the second row onto the fourth row. And I'm also going to add, which by the way doesn't change the determinant at all. I'm also going to add -1 times the second row onto the bottom row, the fifth row. So that's going to turn my determinant. So now I have, look at this down here. Now I have 0, 1, 0, 0, 0. So I have in the second column here, I have all zeros except for 1. So I'm going to now do the cofactor expansion along this second column. And that's going to bring me to here. So it's 1 times -1 to the fourth times this guy, and of course, this is all just 1. Now, the next thing I'm going to do, which by the way, and even before I do the next time, I'm celebrating because I started with a 5x5 and now I only have a 4x4 only. So, but notice the bottom row of this 4x4, you see it right up here. The bottom row has 2 zeros. Now, again, I like picking zeros, things. I like searching out the zeros because it just makes things easier. Now, if I could turn this 3 into a 0, that would be great. And I'm going to turn the 3 into a 0 by adding -1 times the last column onto the first column. So when I do that, the first column becomes 8, -8, 13. All the other columns stay the same, including this one. But look at this. Now look at this bottom row. It's all zeros except for that one. That's pretty awesome, which means, and again, when you add multiples of a column onto another column, it doesn't change the determinant. So therefore, the determinant of the 4 by 4, which is the same as the determinant of the original 5 by 5, is now going to be +1. This is all just +1 times a 3 by 3 determinant. And 3 by 3 determinants are also awesome. And there's all kinds of stuff you can do. Like, for example, if you would just add the first 2 rows, I'm going to get a whole slew of zeros if I do that. Because if I add the first row onto the second row, look what's going to happen. I get, the -8 plus 8 and -1 plus 1, they all become zeros. So let's just do that. Let's add the second row onto the first row, and look at that. So now my first row is 0. Now my first row becomes 0, 0, 5, because 2 plus 3 is 5. Everything else is the same. But now I could just, again, I could go further. I could do more if I want, but it's enough already. We don't have to, we're fine. It's easy, it's easy enough at this point. So I'm just going to do 5 times this determinant. So it's 5 times 1 times the determinant of the stuff that's not in the same row and column as that 5, like we learned last time. -8 times 5 is -40 minus -13, which is +13, so it becomes -27 times 5, which is -135, and that is how the professionals do that. This thus concludes section 3.2. Yay!